Greetings, Panthers. Dr. Augustine. This is part 3 video of calorimetry. I'm going to do one more example of a calorimetry problem. Each one I've done is a little bit different. The first one, if you watch that video, was an example of something like a hot piece of metal dropped into a coffee cup calorimeter, and we tried to figure out the temperature change of the hot piece of metal, or actually we were figuring out the specific heat capacity, but another thing that would be common would be to find the final temperature of that reaction. That was the first example. Second example we did was an actual chemical reaction. So the change in heat, change in enthalpy as a result of a chemical reaction. We looked at a salt dissolving in water, and the salt was an exothermic process. That dissolving process was an exothermic process. That's video number 2 you can watch. This is example number 3. And in this one, we're going to calculate the molar enthalpy of reaction. So again, it's going to be another chemical reaction, and we're trying to calculate what the energy change is for 1 mole of that reaction. This covers, again, chapter 7.5 through 7.8 in Tro's textbook. So this is a specific example of constant pressure, calorimetry problem number 3, molar enthalpy of reaction. So here's the wording of it. Suppose we have 0.562 grams of carbon, graphite. It's burned in a calorimeter at 1 atmosphere pressure, so the pressure does not change. That's why this would be a constant pressure example. Temperature of the calorimeter rises from 25 degrees C to 25.89 degrees C. Heat capacity of the calorimeter is 20.7 kilojoules per degree C. What is the molar enthalpy of reaction? So two steps here to start this process, 2 strategy steps. Step number 1, let's start with a balanced chemical equation. Always a good idea in a chemistry class. First thing we're going to do, and then the second thing we're going to do is we're going to try to figure out this Q total equals 0 equals Q cis plus Q surroundings. So this would be a good place to stop the video if you want. See if you can write down a balanced chemical reaction for this, and then also see if you can figure out what the system and surroundings would be in this description. So the balanced equation is graphite, which is a solid form of carbon, plus oxygen, this is a combustion reaction, yields CO2, gas. And what we're trying to find is delta H of reaction of this particular chemical reaction. We don't know what delta H is. That's what we're trying to find in this problem. So the second thing we want to do is we want to identify what our system and surroundings are. So Q total is equal to 0, equal to Q cis plus Q surround. And as before, I like drawing a picture of what we've got going on here. So we've got a calorimeter of some sort. Maybe we have some kind of chamber in here. We have our carbon in here. And that's going to burn up. It's going to combust. There's water in the calorimeter. And that is going to give off heat to the calorimeter. So the chemical reaction is going to give off heat to the calorimeter. It turns out we have 0.562 grams of carbon. And we don't know much else. We don't know how much water is in there. We don't know how much how big this thing is, but we do know this. The calorimeter itself has a heat capacity of 20.7 kilojoules per degree C. So the reason why we don't know that much is it's all been sort of buried into that piece of information. So this entire calorimeter experiment, the heat capacity, that big capital C, is equal to 20.7 kilojoules per degree C. So we don't need to know how much water there is. We don't need to know how thick the walls of this thing are. All we need to know is this piece of information. So this Q cis plus Q surroundings actually becomes relatively easy. The system is this actual chemical reaction, and the surroundings are the calorimeter. So this 0 is actually equal to Q reaction plus Q calorimeter, and that whole thing is equal to 0. All right, so that is my important equation that I have to deal with. Now, of course, I'm going to rearrange this. I'm going to say negative Q reaction equals to Q calorimeter. And at this point, we want to say, all right, what information do we know? Well, we don't know what this is, but I have the heat capacity of the calorimeter. I also have a temperature change of the calorimeter. So one of my flavors of Q that I have, recall I've got 3 flavors of Q. I've got Q equals MC delta T, and I've got Q equals capital C delta T, and I've got Q sub P is equal to delta H. Those are my three flavors of Q that I have. And if I look at this, this is the one I want to use, right? Because I've got the heat capacity and I've also got a temperature change. So I can substitute that in for the calorimeter. So minus Q reaction is equal to the capital C of the calorimeter times delta T, which is equal to 20.7 kilojoules per degree C times T final minus T initial. Okay, so that's going to be 20.7 kilojoules per degree C times 25.89 degrees C minus 25.00 degrees C. Celsius cancels Celsius, and my answer is going to be left in kilojoules. So minus Q reaction is going to be equal to 18.4 kilojoules. Q reaction is equal to negative 18.4 kilojoules. So this amount of carbon, when it burns, has produced negative 18.4 kilojoules. It's a negative sign, makes sense. It's exothermic. It's giving off its heat. The temperature of the surroundings, the calorimeter, has risen from 25 to 25.89. So that tells us that it's absorbing heat. So that makes sense. It's positive. This is negative. Okay, so that number all makes sense. So how does this number, Q reaction, relate to delta H reaction? All right, and this would be another good chance for you to stop the video, think about this for a second, and see if you can come up with a relationship between this Q reaction that we just found and delta H reaction. And the hint I'm going to give you is we're looking for the molar enthalpy of reaction. So that molar is the key piece of information. So this would be a good time to stop the video and see if you can figure it out. So my third flavor of Q is I know that if I have a constant pressure situation, QP is equal to delta H at a constant pressure. I should probably put is proportional to delta H or is related to delta H. And it's related to it because this one is looking for kilojoules per mole. This is actually kilojoules per gram, kilojoules per a certain amount of grams. So what we've actually found in this problem, we have actually found Q reaction is equal to minus 18.4 kilojoules for every 0.562 grams of carbon. If I had a different amount of carbon, I would have got a different amount of energy out. If I had more carbon, this would have been a bigger number. If I had less carbon, this would have been a smaller number. So it's 18.4 kilojoules for every 0.562 grams of carbon. So hopefully from here, you see where we want to go. I'm going to put 12.01 grams carbon for every 1 mole of carbon. Grams carbon cancels grams carbon, and now I have kilojoules per mole. So when I do this reaction, this is actually equal to minus 393.7 kilojoules per mole of carbon, and using the correct number of significant figures, minus 394 kilojoules per mole. That's Q reaction for a mole, but that's also equal to delta H reaction. Why is it equal to delta H reaction? Because this is a constant pressure. It's 1 atmosphere pressure and the pressure does not change. So because it's a constant pressure, I can set Q equal to delta H. So here's the last step to this problem then. It's minus 394 kilojoules per mole for this reaction. Now we have to look back at the thermochemical equation. So that question mark I have here is it minus 394? And the answer is yes, because there's a 1 out in front of here. If this was not a 1, I'd have to rescale it. But because this is 1 mole of carbon, then that number is actually going to be minus 394 kilojoules. And now my proper thermochemical equation is C, graphite, solid, plus O2, gas, yields CO2 gas, delta H of this reaction is equal to minus 394 kilojoules. Okay, that is how these delta H values are found is by doing an experiment a lot like this one. So by doing an experiment like this, we can find this delta H value and we can set it equal to the balanced chemical equation. All right, hopefully with those 3 different examples that we've done, that will get you a long ways of solving a lot of different calorimetry problems you could find. Thanks for watching.